Greetings. I was looking at different comments on YouTube and seeing people talk about the GEE. And I had some understanding that that was some kind of testing in India, but I was not familiar with that. So I tried to find a practice test or some questions from that. I didn't even know what JEE stood for, but I've since found out. I found a website and started looking through some information and ran across one of the topics that seemed to be some prerequisite knowledge was Apollonius's theorem, and that is a plane geometry theorem, so that definitely got my interest since I really like geometry. So I've got a diagram up here that I'm going to use. This theorem works for any triangle, so when you draw your own sketch of whatever diagram you want to use, don't try to force it into something specific like a right triangle or an equilateral triangle or an isosceles triangle. Try to be scalene so that you have the most weirdness to it, so you don't try to force your assumptions onto your understanding of your proof. The first site that I found had some mistakes in it, it looked like, and it also didn't have diagrams. So if you're not good with taking text and turning it into a diagram, I think you'd have more difficulty in trying to learn from that site. I found another site that had diagrams. I'm going to put the theorem up here for you to look at, and my diagram, and also kind of an algebraic statement of what we're doing. And then I'd like to give a proof for this theorem. I'm not going to try to replicate the proofs that are available on those websites. You can follow the links and check out those websites for yourself if you want to see some alternate proofs. The approach that I took in proving this, I actually used the law of cosines, and I also had, in a part of my proof, you had to know the difference of angles with a cosine function. So those are going to be two prerequisite theorems that you need to be aware of to do the proof of the theorem that I'm going to do here. I would imagine those two theorems are also prerequisite knowledge for this test. Some of the other topics that I saw that you should be aware of for some of the testing that they were doing in India could get pretty involved. So I don't think having to know these two extra theorems to do the proof that I want to do is too much of a burden if you actually are preparing for this test. A couple observations we want to make at the beginning of this. We want to recognize that segment AM is congruent to MB. And the reason for that is you can say definition of the median. The median splits the side opposite the angle into congruent pieces because that's a midpoint. So I suppose you could use definition of midpoint too, but I think definition of median is probably better. So that's the reason why we can recognize that. Another thing that I want to observe is that AMC, that angle, is not congruent, but it is a supplementary angle with BMC. All right, this is a linear pair of angles. I'm going to quote supplement theorem here. All right, so I'm recognizing that this segment and this segment are congruent, and that this angle and this angle are supplementary, meaning they add up to 180 degrees. Those are two important observations that I'm going to make use of. And then I said that I wanted to use the law of cosines. I want to make some statements about side AC and side BC. And this is without loss of generality, because this could have been your focus side with the median coming from B to this side, or this could have been a focus side with A coming from here to this side. So you could, the third side is based on the decisions you make or the givens that you're given. We're not necessarily given a specific side with this theorem. It just states that the sum of the squares of the two sides are going to equal 2 times half the third side squared plus 2 times the median squared. So we're not told which one's the third side. So that decision is up to you. So without loss of generality, I'm kind of using the base as my third side. So those of you that have had more proof background, sometimes you'll see the abbreviation WLOG. This is without loss of generality, meaning we're making a decision, but it's not really going to affect the proof. You can make another decision and your proof results are going to be the same. All right, so this is my third side here, the AB side. So I want to make a statement about AC. AC is this side over here. AC squared is going to be, and I'm going to look at just this triangle right here, this left half of the triangle. So AC is going to be equal to CM squared plus AM squared minus 2 times CM times AM times the cosine of this angle here, which is directly across from side AC. So that is angle AMC. And that's the angle that we recognized up here that added to this other angle was 180 degrees. So at a later part of this proof, the fact that this angle is already a statement up here is going to come into play. Notice also that AM is a segment we've already identified. AM is already in play in 2 different places in this statement. And this is simply plugging in the values here into the law of cosines. All right, this may not seem like the most straightforward proof for this, but this is my proof, and if you want to prove it another way, there's certainly other ways to prove this theorem. There's probably 3 or 4 good ways to prove this theorem. That's a nice thing about this theorem, lots of ways to prove it. All right, I want to make a statement about BC over here. Very similar to what I just did. I want to make a statement. We're talking about BC squared is going to be a part of that sum discussion. So I've got AC squared here. I want something about BC. So I'm going to use law of cosines again. Looking at BC here, I am going to have that MB here squared plus CM here squared minus 2 times MB times CM times the cosine. And since this was our side, the cosine we want is BMC here. All right, notice that this angle is the other angle that's already previously been mentioned in our proof. And this is law of cosines again. So now I want to get the left-hand side of my proof established. I want to know something about this side squared plus this side squared. So look at this. If I take this, I have this statement. I'm going to add this to this. So that means I'm going to add the right-hand side to the right-hand side here. All right, so this plus this, we have AC squared plus BC squared is this plus this. All right, so what I want to do here is I want to look for things that I can simplify now that I have this statement. One thing I want to notice is that AM and BM, according to this very first observation we made, are congruent. So I can substitute either all the BMs can be AMs or all the AMs can be MBs here. Okay, so we can make those substitutions as we need it. And we're going to do that because we want to take advantage of that. I'm going to go ahead and I'm going to take all the MBs and replace it with AMs. So that's going to be one of the substitutions that I do here. So this is going to become AM squared here. This over here will be AM here. So I have AM, 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 AM here. All right. And then the other substitution that I want to make is this right here. This, we know that this angle and this angle added together is 180 degrees. I want to rewrite this angle so that I have AMC in here and also the 180 degrees. Essentially, I'm solving this statement right here for that angle. So if we out to the side do a little bit of side work. So taking this, subtracting this from both sides, I have this statement. So I can replace this with this right here. Right there. So now you see why I wanted that other theorem, the difference of angles for a cosine, because it's going to show up here. All right. Now that I've got my substitutions in here, I'm going to bring the like terms together that I can. I have a cm squared here, cm squared here, am squared here, am squared here. And then notice that I have negative 2am cm and negative 2cm am. I'm going to factor that out. So with those simplifications, I have this. Notice over here at the very beginning, this is the statement that we want to have and be able to keep until the end of the proof, because all of this right now we're saying is equal to AC squared plus BC squared. So if this thing here simplifies to 0, we're done. And that's what's going to happen. We're going to look at what's happening in the parentheses here. And we have this cosine with the different angles here. We need to use that difference of angles theorem for cosine. So we're going to have cosine 180 degrees times the cosine of this angle in here, this angle AMC. To that we have to add the sine of 180 degrees times the sine of the same angle AMC. All right, so that's this piece right here using the difference of angles for cosines. So this one cosine becomes a cosine times cosine plus a sine times a sine. All right, so that's all kind of in big parentheses, and that's being added to this cosine over here. Right, so that's all in parentheses there, and then all of this stuff on the left stays the same. We want to make a couple of observations. The sine of 180 degrees goes to 0, and the cosine of 180 degrees goes to -1. So if you know how to use the unit circle, you can check that real quick. If you need to plug that into your calculator, that's something else you could do. Perhaps you've memorized those. Okay, so what does that give us? That's going to give us this cosine of AMC minus cosine of AMC. So that term right there is going to go to 0. Right there. We're going to have cosine of AMC minus cosine of AMC. Right there. Because this first cosine becomes -1 times this, so that's why there's a subtraction there. So this is going to be 0 here. So this whole piece right here is 0. We have 0 times this angle, so 0 times any real number is going to be 0. So we're going to add to this 0 another 0. So this whole thing in parentheses is 0. So we're going to take that 0 and multiply it by this thing here, which means all of that goes to 0. So that means that we're subtracting 0 from everything here on the left, giving us that AC squared plus BC squared equals 2 times CM squared plus 2 times AM squared. So that's the line that I have right now. I want to go back and look at my diagram and see what I have in this statement going on. I have AC squared plus BC squared is 2 times CM squared plus 2 times AM squared, which was Apollonius's theorem statement. So this is what we wanted. So you can make your proof mark right there. We are done with this proof. This is a true statement, which was the expectation. It seems to have been around for a while. So I have done Apollonius's theorem, triangle theorem here, using the law of cosines, the supplement theorem, and the difference of angles for cosines. Those were prerequisite theorems that I used here, and definition of median was necessary. You had to have a median in your triangle. Of course, this is all done in the plane. This is plane geometry or Euclidean geometry. And there we have it. This was kind of interesting to do. I didn't want to take the same approaches that were shown on the website, and I like to do proofs anyways in a very general idea with the plane geometry where I don't have to assign coordinates to these. I like to be able to work with the diagram directly and then kind of work everything out. So that was one of my goals, was to be able to do that without assigning coordinates and an axis to here. The coordinate proof would be one of the ways that you could prove this, and that was demonstrated on websites. Hopefully this has been interesting and informative. Cheerful calculations.